So in this video we are going to discuss about restricted earth fault protection, which is also called as Aria protection. And well, I have already made a video on this topic, but in this video we are going to discuss this topic in a detailed way. So what you can see on the screen is a simple differential protection circuit of a three-phase transformer, where we have three sets of CTs lying on the primary side of the transformer, three sets of CTs lying on the secondary side of the transformer, and the duty of all these six current transformers is to provide current to the differential coil of the relay when there is a fault within the differential zone of the transformer. So the circuit has been designed in such a way that current will be flowing through all these three coils of differential relay only when there is a fault within the differential zone of the transformer. So when there is a fault within the differential zone, that is the area between the CTs lying on the both sides of the transformer, then only it is going to measure a fault current. Now, for the operation of this relay, there shall be a flow of differential current whose magnitude is more than the pickup value of the current. So for this particular differential relay, let us assume that the pickup value was, let's say it was ID, and if there is a fault within the differential zone of the transformer when there was a differential current flowing through the relay coil whose magnitude was, let's say, IA, and if IA is more than ID, then only the differential relay is going to operate. If IA is less than ID, then the differential relay is not going to operate, because though there is a flow of differential current, but it is less than the pickup value of the differential relay. That's why it is not going to trip, or it is not going to give any trip signal to the circuit breaker lying on the high voltage side of the transformer and the circuit breaker lying on the low voltage side of the transformer. So this is the basic operation of differential relay of a transformer. So if we consider a situation in which there is a fault at this point in the transformer, so it's obvious that here we can see that the full voltage is getting grounded. So if we suppose that here the voltage rating is 220 kV and here it is 33 kV, then here we can see that it's directly 220 kV by root 3 is getting grounded. So in this case, the fault current, which if I'm marking it as IF, will have a very high magnitude. And during that situation, the differential current that is flowing through the differential coil of the differential relay, which I have marked it as IA, will always be higher than the differential relay's pickup current, that is ID. So now if we consider another situation in which there is a fault which is quite near to the neutral of the transformer. So in this particular case, we can see that the voltage that is being grounded is not that high. So the flow of current, that is IF is the fault current, will not have a very high magnitude. So the magnitude may not be that high, or we can just mark it as a low magnitude current. So if during that particular situation, if we consider that the differential current that was flowing through the differential relay was IA, there is a probable chance that this IA is below the differential pickup current, and during that particular situation the differential relay may not operate, or it may not work. So in order to cater that situation, we implement a special kind of protection function which is called as REF, or restricted earth fault protection. So this is how we protect the star side of the transformer when there is an earth fault in the system, but it is of smaller magnitude. But for the delta side of the transformer, since it is connected in delta, if there is a fault, let's say at this point, during that particular situation, there is also a probable chance that the differential relay may not operate. But we do not implement REF protection on the delta side of the transformer, but there is a special way of clearing that particular fault, which is with the help of another relay which is called as common earth fault relay, which is implemented with the help of another transformer which is called as grounding transformer, which is a zigzag transformer, so regarding which we will be discussing in a separate video. But in this particular video, let us just discuss about the REF relay, that is the REF protection. So now talking about the operation of REF relay, the REF protection circuit looks like this, where we have CTs on all the phases of the transformer and connected in this way, and we have a neutral CT. And this is the REF relay which is going to get current from the phase side CTs and the CT from the neutral side. So suppose that there is a fault in the system, it's obvious that the fault current will be rotating in this way, or it will be flowing through the neutral in this way, which is going to have this direction. And the phase side is going to draw current in this way. So the secondary side of the circuit will be something like, in order to balance this current, the current will be flowing in this way in the CT secondary, and it will take up this path. And here, in order to balance this current, the CT secondary current will be flowing in this way, and it is going to take up this path. So if this one is I1 and this one is I2, so the current that is flowing through the REF current, which is marked as IR, is equal to I1 plus I2. So if this I1 plus I2 is greater than the pickup value of REF relay, which is very low, which is set to a very low value, it is going to give a trip signal to the circuit breaker located on the high voltage side of the transformer, and it is going to give trip signal to the circuit breaker located on the low voltage side of the transformer, because if the low voltage side has a connectivity with the system, then it will keep on feeding the fault, which is ultimately going to damage the transformer. So when there is an REF trip, it is going to give trip signal to both side circuit breaker. Now if we consider that there is a fault outside the zone, let's say the fault has taken place at this way, and this way the current will be flowing and it will take up this path. So this is the way the current will be flowing through the CT. So in this particular case we can see that the current that will be flowing through the neutral side CT will have this direction, and here in order to balance that current, the current flowing through this CT, and in this CT the current is having this direction, so in order to balance that, the current will be flowing in this way and it is going to take up this path. So here we can see that if this one is I1 and this one is I2, then the current that is flowing through the REF relay, that is IR, is going to be I1 minus I2, and it will be equal to 0. Thus when there is a fault outside the REF zone, it is not going to give any trip signal, because it is going to treat it as a fault outside the transformer, a fault not within the transformer. So now it is clear that the restricted earth fault protection is going to operate only when there is an earth fault within the restricted area. Outside the restricted area, it is not going to give any trip signal. That's why we call it as restricted earth fault protection. So now talking about the types of area protection that is available to us, we have two types of area protection. The first one is high impedance area protection, and the second one is low impedance. So low impedance area protection is basically implemented with the help of numerical relays. So in order to implement low impedance area protection, we need to have numerical relays. But high impedance area protection is the one which we discussed just now. So this is the circuit of a high impedance area protection, which we will discuss later, that why we call it as high impedance. But the constraint of this protection philosophy, that is high impedance area protection, is that the CT ratio of all these three CTs and this neutral CT should be same. So if we have a CT ratio of this side is, let's say, 400:1, then all the CTs should have 400:1 CT ratio, which is not applicable in low impedance area protection. So in low impedance area protection, this CT, that is the neutral side CT ratio, may be different from the phase side CT ratio. But the CTs which are lying on the phase side, they should have same CT ratio. Means if here we have 400:1 CT ratio, all the phases CT should be 400:1. But this one may be 800:1 or it may be 200:1. There is nothing wrong in it if we are implementing low impedance REF protection. Now another thing, or another difference between high impedance and low impedance REF protection, is about the operation of the relay. So here we can see that it is basically an overcurrent relay which has a setting. So if we have a setting like this, which is the pickup value, let's say that this is the REF pickup, as soon as it comes here, it is going to give a trip signal, it is not going to see anything else. Means that if there is a flow of current through the REF relay which is more than its pickup value, means if this IR which was flowing in the REF relay, if it was more than the REF pickup, then it is going to give trip signal, and if IR is less than the REF pickup, it is not going to give any trip signal. But such is not the case when we implement low impedance REF protection, because the operation is something like this, where we have a restraining current on x-axis and we have differential current on y-axis, and it is going to have an operating characteristic like this. So previously in high impedance REF protection, what we saw is that if the REF current, is the current being measured by the relay, is more than the pickup value, then it is going to give a trip, and if it is below the measured value, and if the current being measured is below the pickup value, it is not going to give any trip. But such is not the case in this low impedance area protection, because here we can see that we have introduced a slope. So now talking about the high impedance area protection, so this is how the high impedance REF protection circuit looks like. Well, in reality we have a metro seal parallel to this combination, but we are not going to discuss anything about the metro seal coil. But in this particular circuit we can see that in addition to this particular relay, we have a resistance which is called as the stabilizing resistance. Now the purpose of this resistance is that it is going to give stability to the relay when there is a fault outside the differential zone or outside the restricted zone, but during that faulty situation one of the CT gets saturated. So let us just consider that there is a massive fault at this particular point in the system. So it's obvious that it is a fault outside the restricted zone of the REF relay, but the fault current was so high that this particular CT gets saturated. So this CT is in saturated condition. So now the fault current that will be flowing in the system will have this particular direction. So due to the saturation of this particular CT, we know that it is not going to show the proper reflection of its primary current on the secondary side of the CT. So if we consider that the current that was flowing in this side of the CT was, let's say it was I is equal to 0, but this CT was not in saturated conditions, so in order to balance that current, it will be having a flow of current on its secondary side, but there is no flow of current on the secondary side of this CT. So it's obvious that this relay is going to operate because there is no balancing by the phase side CT current. So in order to avoid that situation, what we do is we introduce a resistance in series with the relay coil, which is called as the stabilizing resistance, which is going to provide stabilization when there is a fault outside the restricted zone. So in order to understand the significance of stabilizing resistance in a proper way, let us just look at the area protection circuit in a better way. So this is the exact equivalent circuit of area protection, in which we can see that in parallel to this particular CT, we have a component which is called as the magnetizing component. So these all are the magnetizing component of each CT. So if you could remember the equivalent circuit of a current transformer, it is something like this. We have a current source, and in parallel to that we have a magnetizing component. So this magnetizing component is basically a combination of a resistance, and in parallel to that we have an inductance. And the value of this combination, that is Z, is very high. So since it is very high, the CT is going to draw a very minimum amount of magnetizing current. So now, considering situation in which there was a fault outside the restricted earth fault zone, now the magnitude of this current was so massive that this CT got saturated. Now due to saturation of this particular CT, it's obvious that the current that is flowing in this way is going to have a value which is I is equal to 0. But due to saturation, what will happen is that the magnitude of this Z, which was high, will now become low. So now we are having a very low impedance in parallel to this relay, because this relay is parallel to the magnetizing component of all the CTs. We can see that this component, this component, and this component, and this component is parallel to this particular relay. So since the fault current is flowing in the system in this way, and since the CT is in saturated condition, the current that is flowing in this circuit is I is equal to 0. Now here, this is in healthy condition, the current will be flowing in this way. Now some part of this current will flow in this way in order to provide magnetizing current to the CT. And now at this point we can see that since the resistance, or since the impedance, magnetizing impedance, has fallen down, this current is getting divided into two parts. The first part is going in this way and the other will be going in this way. So if the current that is flowing through this relay is more than the pickup value, the relay is going to operate if the CT is getting saturated. But if we introduce a high impedance, which is called as stabilizing resistance, in the circuit, we can see that there will be a flow of current through this path of the relay, but since this is having a very low impedance, the maximum current will take up this path. So the maximum current during faulty situation will be flowing through this path, and this way it will be returning, and a very minimum amount of current will be flowing in this way, because this current is experiencing a very high amount of resistance to it. That's why low amount or minimum amount of current will flow through this path, and the maximum current will be flowing in this way. So this is how, when we implement stabilizing resistance, we avoid the operation of restricted earth fault relay when there is a fault outside the restricted earth fault zone, but one of the CT has got saturated. So now there might be a question that how this relay is going to behave when there is a fault within the zone. So let us suppose that there is a fault at this point, the fault was massive and this CT gets saturated. Then will the relay operate during that particular situation, because the same concept applies here as well. But during that particular situation, the relay is going to operate because this I is equal to 0 will not become instantaneously, but the time delay for the operation of REF relay is 0 milliseconds, means it is instantaneous. So by the time this CT gets saturated, before that itself this relay operates and it gives tripping signal to the circuit breaker. So this is how the high impedance REF protection circuit works. So now the next question of concern is that what is the value of this stabilizing resistance, means how much of resistance shall we introduce in series with the relay coil so that the relay does not mal-operate when there is a fault outside the restricted earth fault zone. So regarding the value of this stabilizing resistance that must be introduced in the circuit in order to have a stable area of protection when there is a through fault and one of the CT gets saturated, in order to know that we have to carry out fault analysis in the system. So suppose that there is a fault at this point, we have to know the maximum fault current that can flow. So let us suppose that there is a fault at this point and the maximum fault current that will be fed in this way is 8000 amperes. So 8000 amperes is the maximum fault current that will be flowing, and during that situation this CT gets saturated. So let us just assume that CT ratio of all these CTs should be 1 and its value is 200:1. So in secondary the magnitude of current that will be flowing, or the fault current in secondary, has a value which is equal to 8000 divided by 200, so whose value is 40 amperes. So it's obvious that in this circuit the current that will be flowing will have this direction and its magnitude is 40 amperes, and this CT is in saturated condition. It is not going to feed any current, so the magnitude of current that will be flowing here will be I is equal to 0. But this CT has a CT ratio because of its winding, so let us just assume that the CT ratio of this CT is RCT is equal to 1 ohm, and this CT is connected or coming to the relay through this cable. So the value of resistance of this cable is, let's say, it's 10 ohms. So what we are supposed to do is that the circuit should be designed in such a way that the maximum fault current flows in this way and it keeps on rotating in this way, and the minimum amount of current will be flowing through the REF relay coil, because we are not supposed to have any operation from the REF relay during this particular situation. So what we have to do is that during this particular situation we have to find the voltage that is appearing across this relay circuit, means the voltage that is getting developed across the series combination of this stabilizing resistance and the relay. So during this particular situation the voltage that will develop across this circuit is equal to 40 into 1 plus 10 into 2, which is equal to 20. So the voltage that will develop across this circuit is 21 into 40 is equal to 840 volts. So the magnitude of this voltage which is getting developed across the series combination of stabilizing resistance and the relay coil, which is 840 volts in this case, should be less than or equal to 1 by 2 of the knee point voltage of the CTs, because we are taking a safety factor of 2 so that we can avoid CT saturation due to a problem in the CT secondary circuit. So in this case the voltage that is getting developed is 840 volts, and let us suppose that the pickup value of this relay is equal to zero point 0.1 amperes, that is 100 milliamperes is the pickup value of that relay current. So the magnitude of stabilizing resistance will be 840 divided by 1, which is equal to 8.4 kilo ohms. So this is the amount of stabilizing resistance that should be kept in the circuit. Actually it is 8.4 kilo ohms minus the resistance of this relay coil, but it is quite low, so we can just give the stabilizing resistance value to be 8.4 kilo ohms. So this is how we calculate the value of stabilizing resistance which should be introduced in the area protection circuit in order to keep it stable during a through fault situation, considering the CT saturation cases. So now talking about the minimum fault current that should flow in the primary circuit so that the RF relay operates satisfactorily. Well, in order to know that, let us just take this circuit and let us assume that this side of the transformer has no connection with the system. So here the breaker is in open condition, and from this side, means the secondary side or the primary side of the transformer, let us just consider that it is connected in delta but it has been charged. So means there is a supply of voltage on the delta side of the transformer, then we say that it is in charged condition, and once we close the circuit breaker and we put load to it, it is going to draw current from the system. But in this situation it is going to draw only the magnetizing current. But if a fault takes place, then it's obvious that the fault current will be drawn by the transformer from the system. So in this particular situation, let us just assume that there is a fault at this point. So it's obvious that no current is going to flow because neutral is getting grounded for the second time, and and there is no voltage which can drive the fault current. But suppose that there is a fault at this point, then it's obvious that there is some voltage which is going to drive the flow of fault current. But it's not that for every fault the relay is going to operate, because there should be some minimum amount of fault current that should flow for the satisfactory operation of relay. So suppose that the fault has taken place at this point, so it's obvious that there will be no flow of current from this side. So the current that will be fed in this way is I is equal to 0, and the only current that will be flowing in the system is through this neutral, and this way it will keep on rotating because we have a source only from this side and there is no source from this side of the system. So this current is flowing in this direction, and so in order to balance this current, the current that will flow in this CT secondary will be having this direction. Now this current is taking care of all the resistances or impedances which are connected in parallel to the circuit. So this current is giving current to this circuit, then it is providing current to the magnetizing path of this CT, this CT, this CT, and its own CT. So if the pickup of this relay was 0.1 amperes and the magnetizing current that is drawn by the CTs is, let's say, 10 milliamperes, so 10, 10, 10 and 10, that is total of 40 milliamperes will be fed by this. So for satisfactory operation of the REF relay, the magnitude of this current should be equal to the operating current for the relay coil, that is 0.1 plus 4 times the magnetizing current, or 40, which is plus the total magnetizing current, which is 40 milliamperes in this case. So a total of 0.140 amperes or 140 milliamperes current should flow, or should be the magnitude of this current. So the magnitude of this current, or the current fault current in the primary side of the circuit, will be equal to 200 into 0.140, which is equal to 28 milliamperes. So the magnitude of this fault current should be 28 amperes, then only the relay is going to operate. If it is below 28 amperes, then it is not going to operate. So this is the minimum value of fault current that should flow in the system so that the RF relay is going to operate in a proper way. So this was all about the REF protection of a transformer. Now before we bring REF protection into service, we have to perform some tests on the REF circuit, which is known as the stability of the REF relay. So let us see how are we going to perform REF stability test. So well, for that what we have to do is we simply have to short all these terminals which are lying outside the CT, means the terminals after the CT, and then we are going to apply a single phase AC in this way. And let's say that the magnitude of that AC is 230 volts, and we are simply going to ground this, or we can just connect it with the neutral, because the neutral is already in grounded condition. If we are grounding it, then this is the way it is going to allow the flow of fault current, or it is going to allow the flow of current, and it will flow in this way, and this way it is going to return. So this is also known as zero sequence stability, or it is called as the Aria of stability. So let us suppose that this is drawing a current whose magnitude is I0. It's obvious that its angle is I at an angle of 0 degrees. Here also it is going to be I0 at an angle of 0 degrees, because the source is a single phase supply, and here also it is I0 at an angle of 0 degrees. So it's obvious that all these three currents are getting added up at this point, and this is flowing through this way, and it is taking the path of the ground, and it is returning to the system, or it is returning to the source. So the magnitude of this current is simply sum of all these three currents, which is 3 times of I0 at an angle of 0 degrees, which I am just marking it as 3I0, and this way it is returning, and the magnitude of this current is 3I0. So in order to perform RF stability, what you have to do is we simply have to short this stabilizing resistance in order to have proper reading. So in this particular case, we can see that the current that will be flowing in the circuit will have this direction for the CT secondary, or CT for the CT secondary side, and this way it is getting added up. So 3I0 will be added up in this way, and in order to balance this current, the current will be flowing in this direction whose magnitude is, it's obvious that it is the step down value of 3I0, so I am marking this one as small 3I0, and here also it is small 3I0, because the CT ratio is same. So this is flowing in this direction, and this one is flowing in this direction. So in this case, if we are measuring the current flowing through this cable, it should be equal to I is equal to 0 amperes. But if there is any problem with the circuit, then the value of this I is not going to be 0, but Apart from this, what we are going to do is we are simply going to interchange the CT terminals. Well, for that what you have to do is we just have to open this terminal and it will be connected in this way, and this one will be connected in this way, and the equivalent circuit will be something like this. So in order to balance this current, the current will take up this path, and this way it is flowing now, and here we can see that this 3I0 and this 3 small I0 is getting added up. Now we are going to measure some current which will be 2 times of 3I0 flowing through the relay, and in this case the relay is going to operate. So this is the way we are going to perform Aria of stability or zero sequence stability on the star side of the transformer. So this was all about the operation of this was all about Aria protection and Aria circuit. But in my previous video on basics of Aria protection, there were certain comments regarding the flow of current in the secondary side of the CT when the CT is in saturated condition. So we say that the CT current is going to be zero during CT saturation. We consider that the current will be zero because during that condition, the situation is going to be the worst. So we just take the worst situation, that no current is being fed by the CT, and we are doing all the calculations, because if there is any flow of current, then it's obvious that it is going to balance it out. But if it is zero, then the condition is going to be the worst one. However, during practical situation, the CT secondary current is not exactly zero when it is suffering from CT saturation, but it is having some value. And if we look at some of the simulation results, the CT secondary current is something like this when it is suffering from CT saturation, which has considered some offset as well. And there is the second case where there is no offset. During that situation, the CT secondary current is something like this, where we can see that it is coming to zero, but it has some spikes as well. And here is the third case where the secondary current is something like this when it is suffering from CT saturation. So this is the real time picture, or this is a result of a simulation, but we consider the CT secondary current to be zero during CT saturation, because when we are considering the value of current to be zero, we are simply considering the situation to be the worst one, because if it is not getting zero, then it's obvious that it's not changing its direction. So during that situation, it is trying to balance the current, but when it is falling to zero, then that is creating the worst possible situation. So whenever we are considering CT saturation for the purpose of designing any protection circuit, we consider it to be zero, or we just consider the CT secondary current to be zero. So this was all about area protection, its theory, operation and working, and about CT saturation.